Learning objectives. In this chapter, the user will learn the following in detail. Polygon meshes, representing polygon meshes, consistency of polygon mesh representations, plane equations, parametric cubic curves, Hermite curves, Bezier curves, uniform non-rational B-splines, subdividing curves, drawing curves, comparison of the cubic curves, parametric bicubic surfaces. Bezier curves. The Bezier form of a cubic polynomial curve segment, named after Pierre Bezier, indirectly specifies the endpoint tangent vector by specifying two intermediate points that are not on the curve, as per the figure shown. The figure shows two Bezier curves and their control points. Notice that the convex hulls of the control points, shown as dashed lines, do not need to touch all four control points. The starting and ending tangent vectors are determined by the vectors P1, P2 and P3, P4 and are related to R1 and R4 by the equation shown. The Bezier curve interpolates the two end control points and approximates the other two. The Bezier geometry vector GB, consisting of 4 points, is GB equals matrix P1, P2, P3, P4. Then the matrix MHB that defines the relation GH equals MHB and GB between the Hermite geometry vector GH and the Bezier geometry vector GB is just a 4x4 matrix in the following equation, which rewrites in the matrix form as given below. Bezier basis matrix MB equals MH and MHB gives the following. And the product Q of T equals T and MB and GB as shown below. Q of T equals 1 minus T cubed into P1 plus 3T into 1 minus T whole squared into P2 plus 3T squared to 1 minus T into P3 plus T cubed into P4. The four polynomials BB equals T and MB, which are the weights in this equation, are called the Bernstein polynomials and are shown in this figure. The Bernstein polynomials, which are the weighting functions for Bezier curves, at t equals 0, only BB is non-zero, so the curve interpolates P1. Similarly, at t equals 1, only BB4 is non-zero, and the curve interpolates P4. This figure shows two Bezier curve segments with a common endpoint. G1 continuity is provided at the endpoint when P3 minus P4 equals K into P4 minus P5, with K being greater than 0. Two Bezier curves joined at P4. Points P3, P4 and P5 are collinear. That is, the 3 points P3, P4 and P5 must be distinct and collinear. In the more restrictive case, when K equals 1, there is C1 continuity in addition to G1 continuity. If we refer to the polynomials of two curve segments as XL for the left segment and XR for the right segment, we can find the conditions for C0 and C1 continuity at their join point, as given below. Working with the X component, we have, as given below. As always, the same conditions are true of Y and Z. Thus, we have C0 and C1 continuity when P4 minus P3 equals P5 minus P4 as expected. Examining the four BB polynomials, we note that their sum is everywhere unity and that each polynomial is everywhere non-negative for 0 less than or equal to t less than 1. Thus, QT is just a weighted average of the four control points. This condition means that each curve segment, which is just the sum of four control points weighted by the polynomials, is completely contained in the convex hull of the four control points. The convex hull for 2D curves is a convex polygon formed by the four control points. Think of it as a polygon formed by putting a rubber band around the points. For 3D curves, the convex hull is a convex polyhedron formed by the control points. Think of it as a polyhedron formed by stretching a rubber sheet around the 4 points. This convex hull property holds for all cubics defined by the weighted sums of control points if the blending functions are non-negative and sum to 1. In general, the weighted average of n points falls within the convex hull of the n points. This can be seen intuitively for n equals 2 and n equals 3, and the generalization follows. Another consequence of the fact that the four polynomials sum to unity is that the value of the fourth polynomial for any value of t can be found by subtracting the first three from unity. The convex hull property is also useful for clipping curve segments. Rather than clip each short line piece of a curve segment to determine its visibility, we first apply a polygonal clip algorithm to clip the convex hull or its extent against the clip region. If the convex hull extent is completely within the clip region, so is the entire curve segment. If the convex hull extent is completely outside the clip region, so is the curve segment. Only if the convex hull extent intersects the clip region does the curve segment itself need to be examined. Comparison of the cubic curves. The different types of parametric cubic curves can be compared by several different criteria, such as ease of interact manipulation, degree of continuity at joint points, generality, and speed of various computations using the representations. Of course, it is not necessary to choose a single representation since it is possible to convert between all representations. For instance, non-uniform rational B-splines can be used as an internal representation, while the user might interactively manipulate Bezier control points or Hermite control points and tangent vectors. Some interactive graphics editors provide the user with Hermite curves while representing them internally in the Bezier form supported by a PostScript. In general, the user of an interactive CAD system may be given several choices such as Hermite, Bezier, uniform B-splines, and non-uniform B-splines. This table compares most of the curve forms. Number of parameters controlling a curve segment is the four geometrical constraints plus other parameters such as knot spacing for non-uniform splines, beta 1 and beta 2 for B-splines, or A, B, or C for the Kochanek-Bartels case. Continuity easily achieved refers to constraints such as forcing control points to be collinear to allow G1 continuity. Because Cn continuity is more restrictive than Gn, any form that can attain Cn can, by definition, also attain at least Gn. When only geometric continuity is required, as is often the case for CAD, the choice is narrowed to the various types of splines, all of which can achieve both G1 and G2 continuity. Of the three types of splines in the table, uniform B-splines are the most limiting. The possibility of multiple knots afforded by non-uniform B-splines gives more shape control to the user, as does the use of the beta 1 and beta 2 shape parameters of the beta splines. It is customary to provide the user with the ability to drag control points or tangent vectors interactively, continually displaying the updated spline. One of the disadvantages of B-splines in some applications is that the control points are not on the spline itself. When the user selects a knot and moves it by some delta x, delta y, the control point weighted most heavily in determining the position of a joint point is also moved by delta x and delta y. The joint does not move the full delta x, delta y because it is a weighted sum of several control points, only one of which was moved. Therefore, the cursor is repositioned on the joint. This process is repeated in a loop until the user stops dragging. Drawing curves. There are two basic ways to draw a parametric cubic. The first is by iterative evaluation of x of t, y of t, and z of t for incrementally spaced values of t, plotting lines between successive points. The second is by recursive subdivision that stops when the control points get sufficiently close to the curve itself. Simple brute force iterative evaluation display was described where the polynomials were evaluated as successive values of t using Horner's rule. The cost was 9 multiplies and 10 additions per 3D point. A much more efficient way repeatedly to evaluate a cubic polynomial is with forward differences. The forward difference delta ft of a function ft is delta f of t equals f of t plus delta minus f of t with delta greater than 0, which can be rewritten as f of t plus delta equals f of t plus delta ft. Rewriting the above equation in iterative terms, we have f of n plus 1 equals fn plus delta fn, where f is evaluated at equal intervals of size delta so that tn equals n into delta and fn equals f of tn. For a third degree polynomial, f of t equals at cubed plus bt squared plus ct plus d equals t and c. So the forward difference equation is as shown on the screen. Thus, delta ft is a second degree polynomial, but forward differences can be applied to delta ft to simplify its evaluation. We write delta squared ft equals delta of delta ft equals delta f of t plus delta minus delta f of t. Applying this to equation of forward difference, and it gives delta squared f of t equals 6a delta squared t plus 6a delta cubed plus 2b delta squared. This is now a first degree equation in t. Rewriting and using the index n, we obtain delta squared fn equals delta fn plus 1 minus delta fn. Reorganizing and replacing n by n minus 1 yields delta fn equals delta fn minus 1 plus delta squared fn minus 1. Now to evaluate delta fn, we evaluate delta squared fn minus 1 and add it to delta fn minus 1. Because delta squared f minus 1 is linear in t, this is less work than evaluating delta fn directly from second degree polynomial. Delta cubed f of t equals delta into delta squared f of t equals delta squared f of t plus delta minus delta squared f of t equals 6a delta cubed. The third forward difference is a constant, so further forward differences are not needed. Rewriting with n and with delta cubed fn as constant yields, we get delta squared fn plus 1 equals delta squared fn plus delta cubed fn equals delta squared fn plus 6a delta cubed. On a further rewrite, replacing n with n minus 2 completes the development. Delta squared fn minus 1 equals delta squared fn minus 2 plus 6a delta cubed. This result can be used to calculate delta fn, used to find fn plus 1. To use the forward differences in an algorithm that iterates from n equals 0 to n delta equals 1, we compute the initial conditions for t equals 0. They are f naught equals d, delta f naught equals a into delta cubed plus b delta squared plus c delta, comma, delta squared f naught equals 6a delta cubed plus 2b delta cubed, comma, delta cubed f naught equals 6a delta cubed. These initial condition calculations can be done by direct evaluation of the four equations. Note that, however, if we define the vector of initial differences as d, then d can be represented by the matrix shown. Rewriting with the 4x4 matrix represented as E of delta yields d equals E of delta into c. Because we are dealing with three functions, x of t, y of t, and z of t, there are three corresponding sets of initial conditions. Dx equals E delta Cx, dy equals E delta Cy, and dz equals E delta Cz. Based on this derivation, the algorithm for displaying a parametric cubic curve is given in this figure. This procedure needs just 9 additions and no multipliers per 3D point, and just a few adds and multipliers are used for initialization. This is considerably better than 10 additions and 9 multipliers needed for the simple brute force iterative evaluation using Homer's rule. Notice that error accumulation can be an issue with this algorithm, and sufficient fractional precision must be carried to avoid it. For instance, if n equals 64 and integer arithmetic is used, then 16 bits of fractional precision are needed. If n equals 256, 22 bits are needed. Recursive subdivision is the second way to display a curve. Subdivision stops adaptively when the curve segment in question is flat enough to be approximated by a line. The general algorithm is given in this figure. The Bezier representation is particularly appropriate for recursive subdivision display. Subdivision is fast, requiring only 6 shifts and 6 adds. The test for straightness of a Bezier curve segment is also simple, being based on the convex hull formed by the 4 control points as per the figure shown. If the larger of distances d2 and d3 is less than some threshold epsilon, then the curve is approximated by a straight line drawn between the endpoints of the curve segment. For the Bezier form, the endpoints are P1 and P4, the first and last control points. Were some other form used, the flatness test would be more complicated and the endpoints might also have to be calculated. Thus, conversion to Bezier form is appropriate for display by recursive subdivision. If the subdivision is done with integer arithmetic, less fractional precision is needed than in the forward difference method. If at most 8 levels of recursion are needed, a reasonable expectation, only 3 bits of fractional precision are necessary. If 16, 4 bits. Recursive subdivision is attractive because it avoids unnecessary computation, whereas forward differencing uses a fixed subdivision. The forward difference step size delta must be small enough that the portion of the curve with the smallest radius of curvature is approximated satisfactorily. For nearly straight portions of the curve, a much larger step size would be acceptable. A hybrid approach, adaptive forward differencing, uses the best features of both the forward differencing and subdivision methods. The basic strategy is forward differencing, but an adaptive step size is used. Computationally efficient methods to double or half the step size are used to keep it close to 1 pixel. This means that essentially no straight line approximations are used between computed points. Hermite curves. The Hermite form, named for the mathematician, of the cubic polynomial curve segment is determined by constraints on the endpoints P1 and P4 and tangent vectors at the endpoints R1 and R4. The indices 1 and 4 are used. To find the Hermite basis matrix MH, which relates the Hermite geometry vector GH to the polynomial coefficients, we write 4 equations, one for each of the constraints in the 4 unknown polynomial coefficients, and then solve for the unknowns. Defining GHX, the x component of the Hermite geometry matrix, as shown, and rewriting x of t as x of t equals ax t cubed plus bx t squared plus cx, t plus dx equals t and cx equals t and mh and ghz equals t cubed t squared t and 1 mh and ghx. The constraints on x0 and x1 are found by direct substitution as shown. The tangent vector constraint equations can be written as shown. The above 4 constraints can be rewritten in matrix form as shown. For this equation and the corresponding expressions for y and z to be satisfied, MH must be the inverse of the 4 by 4 matrix, as shown. MH, which is of course unique, can now be used in x of t equals t and mh and ghx to find x of t based on the geometry vector ghx. Similarly, y of t equals t and mh and ghy, and z of t equals t and mh and ghz. So we can write q of t equals x of t, y of t, z of t equals t and mh and gh, where gh is a column vector. P1, P4, R1, R4. Expanding the product t and mh and q of t equals t and mh and gh gives the Hermite blending functions bh as the polynomials weighting each element of the geometry vector, as shown below. This figure shows the four blending functions. Notice that at t equals 0, only the function labeled p1 is non-zero. Only p1 affects the curve at t equals 0. As soon as t becomes greater than 0, R1, P4 and R4 begin to have an influence. The figure shows the Hermite blending functions labeled by the elements of the geometry vector that they weight. This figure shows the four functions weighted by the y components of a geometry vector, their sum y of t and the curve q of t. A Hermite curve showing the four elements of the geometry vector weighted by the blending functions leftmost four curves, their sum y of t, and the 2D curve itself, far right, x of t, is defined by a similar weighted sum. This figure shows a series of Hermite curves. The only difference among them is the length of the tangent vector, r1. The directions of the tangent vectors are fixed. The longer the vectors, the greater the effect on the curve. This figure shows a family of Hermite parametric cubic curves. Only r1, the tangent vector at p1, varies for each curve, increasing in magnitude for the higher curves. This figure is another series of Hermite curves with constant tangent vector lengths but with different directions. This figure shows a family of Hermite parametric cubic curves. Only the direction of the tangent vector at the left starting point varies. All tangent vectors have the same magnitude. A smaller magnitude would eliminate the loop in the one curve. In an interactive graphic system, the endpoints and tangent vectors R1 of the curve are manipulated interactively by the user to shape the curve. This figure shows one way of doing this. The two Hermite cubic curve segments displayed with control to facilitate interactive manipulation. The endpoints can be repositioned by dragging the dots, and the tangent vectors can be changed by dragging the arrowheads. The tangent vectors at the join point are constrained to be collinear to provide C1 continuity. The user is usually given a command to enforce C0, C1, G1, or no continuity. The tangent vectors at the t equals 1 end of each curve are drawn in the reverse of the direction used in the mathematical formulation of the Hermite curve for clarity and more convenient user interaction. For two Hermite cubics to share a common endpoint with G1 geometrical continuity as in this figure, the two Hermite curves joined at P4. Tangent vectors at P4 have the same direction but different magnitudes, yielding G1 but not C1 continuity. The geometry vectors must have the form as shown below. There must be a shared endpoint P4 and the tangent vectors with at least equal directions. The more restrictive condition of C1 parametric continuity requires that k equals 1, so the tangent vector direction and magnitude must be equal. Hermite and other similar parametric cubic curves are simple to display. This figure gives the code. The evaluation within the begin end takes 11 multiplies and 10 additions per 3D point. Use of Horner's rule for factoring polynomials. F of t equals at cubed plus bt squared plus ct plus d equals at plus b into t plus c whole bracketed into t plus d. Reduces the effort slightly to 9 multiplies and 10 additions per 3D point. Because the cubic curves are linear combinations, weighted sums of the four elements of the geometry vector. We can transform the curves by transforming the geometry vector and then using it to generate the transformed curve, which is equivalent to saying that the curves are invariant under rotation, scaling, and translation. This strategy is more efficient than is generating the curve as a series of short line segments and then transforming each individual line. Parametric bicubic surfaces. Parametric bicubic surfaces are a generalization of parametric cubic curves. The general form of the parametric cubic curve Q of t equals t and m and g, where g is a geometry vector, is a constant. First, for notational convenience, we replace t with s, giving Q of s equals s and m and g. If we now allow the points in G to vary in 3D along some path that is parameterized on T, we have the following representation. Now, for a fixed T1, Q of S, T1 is curve because G of T1 is constant. Allowing T to take on some new value T2, where T2 minus T1 is very small, Q of ST is a slightly different curve. Repeating this for arbitrarily many other values of T2 between 0 and 1, an entire family of curves is defined, each arbitrarily close to another curve. The set of all such curves defines a surface. If the GI of T are themselves cubics, the surface is said to be a parametric bicubic surface. Continuing with the case that the GI of T are cubics, each can be represented as GI of T equals T and M and GI, where GI equals GI1, GI2, GI3, GI4 transpose. The capital G and small g are used to distinguish from the G used for the curve. Hence, GI1 is the first element of the geometry, vector for curve GI of T, and so on. Now let us transpose the equation GI of T equals T and M and GI using the identity A and B and C transpose equals C transpose and B transpose and A transpose. The result is GI of T equals GI transpose, M transpose and T transpose equal to GI1, GI2, GI3, GI4 and M transpose and T transpose. If we now substitute this result in each of the 4 points, we have the following resulting matrix. Or Q of S T equals S and M and G and M transpose and T transpose, where 0 is less than or equal to S and T is less than or equal to 1. Written separately for each of X, Y and Z, the form is X of S and T equals S and M and GX and MT and TT. Y of ST equals S and M and GY and M transpose and T transpose. Z of ST equals S and M and GZ into M transpose and T transpose. Given this general form, we now move on to examine specific ways to specify surfaces using different geometry matrices. Hermite surfaces. Hermite surfaces are completely defined by a 4x4 geometry matrix GH. We further elaborate the derivation here, applying it just to X of ST. First we replace T by S to get X of S equals S and MH and GHX. Rewriting this further so that the Hermite geometry vector GHX is not constant but is rather a function of T, we obtain the functions P1x of T and P4x of T define the x components of the starting and the ending points for the curve in parameters. Similarly, R1x of T and R4x of T are the tangent vectors at these points. For any specific value of T, there are 2 specific endpoints and tangent vectors. This figure shows P1T and P4T and the cubic in S that is defined when T equals 0.0, 0.2, 0.4, 0.6, 0.8 and 1.0. The surface patch is essentially a cubic interpolation between P1T equals Q0, T and P4T equals Q1, T, or alternatively between Qs, 0 and Qs, 1. In the special case that the four interpolants Q01, Q1t, Qs0 and Qs1 are straight lines, the result is a ruled surface. If the interpolants are also coplanar, then the surface is a four-sided planar polygon. Continuing with the derivation, let each P1t, P4t, R1t and R4t be represented in the Hermite form as shown. These four cubics can be rewritten together as a single equation, where GHX is in the matrix form shown. Transposing both sides, the result is as follows. Substituting this in equation of x of s, t yields x of s, t equals s and mh and gh and mth and tt. Similarly, y of st and z of st are given by this equation shown. The three 4x4 matrices GHX, GHY, GHZ play the same role for Hermite surfaces as did the single matrix GH for curves. The element G11x is x 0, 0 because it is a starting point for P1x of t, which is in turn the starting point for x s, 0. Similarly, G12x is x 01 because it is the ending point of P1x of t, which is in turn the starting point for x of s, 1. Furthermore, G13 is dx by dt 0, 0 because it is a starting tangent vector for P1x of t, and G33x is d squared x by ds by dt 0, 0 because it is a starting tangent vector of R1x of t, which in turn is a starting slope of x of s, 0. Using these interpretations, we can write GHX as the upper left 2x2 portion of GHX contains the x-coordinates of the four corners of the patch. The upper right and lower left 2x2 areas give the x-coordinates of the tangent vectors along each parametric direction of the patch. The lower right 2x2 portion has at its corners the partial derivatives with respect to both s and t. These partials are often called the twists because the greater they are, the greater the corkscrew-like twist at the corners. This figure shows a patch whose corners are labeled to indicate these parameters. This Hermite form of the bicube patches is an alternative way to express a restricted form of the cones patch. These more general patches permit boundary curves and slopes to be any curves. Just as the Hermite cubic permits C1 and G1 continuity from one curve segment to the next, so too the Hermite bicubic permits C1 and G1 continuity from one patch to the next. First, to have C0 continuity at an edge, the matching curves of the two patches must be identical, which means the control points for the two surfaces must be identical along the edge. The necessary conditions for C1 continuity are that the control points along the edge and the tangent and twist vectors across the edge be equal. For G1 continuity, the tangent vector requirement is relaxed so that the vectors must be in the same direction but do not need to have the same magnitude. If the common edge for patch 1 is at s equals 1 and that for patch 2 is at s equals 0 as shown in the figure, then the values in some rows of the geometry matrices for the two patches must reflect the G1 conditions as indicated here. Entries marked with a dash can have any value. If four patches joined at a common corner and along the edges emanating from that corner are to have G1 continuity, then the relationships are more complex. Bezier surfaces. The Bezier bicubic formulation can be derived in exactly the same way as the Hermite cubic. The results are as shown. The Bezier geometry matrix G consists of 16 control points as shown in this figure. Bezier surfaces are attractive in interactive design for the same reason as Bezier curves are. Some of the control points interpolate the surface, giving convenient precise control, whereas tangent vectors also can be controlled explicitly. When Bezier surfaces are used as an internal representation, their convex hull property and easy subdivision are attractive. C0 and G0 continuity across patch edges is created by making the four common control points equal. G1 continuity occurs when the two sets of four control points on either side of the edge are collinear with the points on the edge. In this figure, the following sets of control points are collinear and define four line segments whose lengths all have the same ratio, K, is to P13, P14, P15, P23, P24, P25, P33, P34, P35, and P43, P44, P45. An alternative way to maintain interpatch continuity requires that at each corner of an edge across which continuity is desired, the corner control points and the control points immediately adjacent to the corner be coplanar. B-spline surfaces. B-spline patches are represented as shown. C2 continuity across the boundaries is automatic with B-splines. No special arrangements of control points are needed except to avoid duplicate control points which create discontinuities. Bicubic non-uniform and rational B-spline surfaces and other rational surfaces are similarly analogous to their cubic counterparts. All the techniques for subdivision and display carry over directly to the bicubic case. Normals to surfaces. The normal to a bicubic surface needed for shading, for performing interference detection in robotics, for calculating the offsets for numerically controlled machining, and for doing other calculations is easy to find. The S-tangent vector of the surface Q of S, T is, and the T-tangent vector is given by the equations below. Both tangent vectors are parallel to the surface at the point S, T, and therefore their cross product is perpendicular to the surface. Notice that if both tangent vectors are 0, the cross product is 0 and there is no meaningful surface normal. Each of the tangent vectors is of course 3-tuple represents the x, y, z components of the bicubic. With the notation xs for the x component of the S tangent vector, ys for the y component and zs for the z component, the normal is as per the equation shown. The surface normal is a biquintic, that is, two-variable fifth-degree polynomial and hence is fairly expensive to compute. Displaying bicubic surfaces. Like curves, surfaces can be displayed either by iterative evaluation of the bicubic polynomials or by subdivision, which is essentially an adaptive evaluation of the bicubic polynomials. We consider first iterative evaluation and then subdivision. Iterative evaluation is best suited for displaying bicubic patches in the style of this figure shown. Each of the curves of constant S and constant R on the surface is itself a cubic, so display of each of the curves is straightforward as in this figure. Figure shows the procedure to display bicubic patch as a grid. Procedures X, ST, Y, ST and Z, ST evaluate the surface using the coefficient matrix coefficients. Brute force iterative evaluation of for surfaces is even more expensive than for curves because the surface equations must be evaluated about 2 by delta squared times for delta equals 0.1. This value is 200. For delta equals 0.01, it is 20,000. These numbers make the alternative forward differencing even more attractive than it is for curves. Surface subdivision is done by splitting the surface along one parameter, say S, and then splitting each of the two resulting surfaces along T. The curve splitting methods are applied to each set of 4 control points running in the direction of the parameter along which the split is being made. This figure shows the idea with the resulting 4 surfaces labeled LL, LR, RL, and RR. Alternatively, the patch can be split along only one parameter if the patch is locally flat along the other parameter. One critical problem with adaptive subdivision is the possibility of cracks between approximating quadrilaterals as seen in this figure. The cracks occur because of the different levels of subdivision applied to adjoining patches. They can be avoided by subdividing to a fixed depth or by making the flatness threshold epsilon very small. Both solutions cause needless subdivisions. Another way to avoid cracks is to modify adjoining approximating quadrilaterals as suggested in this figure. Figure shows crack elimination in recursive subdivision. A naive algorithm displays quadrilaterals A, B, C, E, E, F, G, D, and G, D, C, H. A more sophisticated algorithm displays quadrilaterals A, B, C, E, E, F, G dash, and G, D dash, C, H. Vertex D dash is used instead of D. The best way to display the quadrilateral as a shaded surface is to subdivide it further into 4 triangles as shown in this figure. This strategy avoids visual artifacts. Quadric surfaces. The implicit surface equation of the form defines the family of quadric surfaces. Quadric surfaces are particularly useful in specialized applications such as molecular modeling and have also been integrated into solid modeling systems. Hence, the implicit quadratic equation is an alternative to rational surfaces if only quadric surfaces are being represented. Other reasons for using quadrics include ease of computing the surface normal, testing whether a point is on the surface, computing z given x and y, and calculating intersections of one surface with another. Parametric cubic curves. Polylines and polygons are first-degree piecewise linear approximations to curves and surfaces, respectively. Unless the curves or surfaces being approximated are also piecewise linear, large numbers of endpoint coordinates must be created and stored to achieve reasonable accuracy. Interactive manipulation of the data to approximate a shape is tedious because many points have to be positioned precisely. The general approach is to use functions that are of a higher degree than are the linear functions. 1. One can express y and z as explicit functions of x so that y equals f of x and z equals g of x. The difficulties with this are that it is impossible to get multiple values of y for a single x, so curves such as circles and ellipses must be represented by multiple curve segments. Such a definition is not rotationally invariant. To describe a rotated version of the curve requires a great deal of work and may in general require breaking a curve segment into many others. And describing curves with vertical tangents is difficult because a slope of infinity is difficult to represent. We can choose to model curves as solutions to implicit equations of the form f of x, y, z equals 0. This is fraught with its own perils. First, the given equation may have more solutions than we want. For example, in modeling a circle, we might want to use x squared plus y squared equals 1, which is fine. But how do we model a half circle? We must add constraints such as x is greater or equal to 0, which cannot be contained within the implicit equation. Furthermore, if two implicitly defined curve segments are joined together, it may be difficult to determine whether their tangent directions agree at the joint point. Tangent continuity is critical in many applications. These two mathematical forms do permit rapid determination of whether a point lies on the curve or on which side of the curve the point lies. Normals to the curve are also easily computed. The parametric representation for curves. x equals x of t, y equals y of t, z equals z of t overcomes the problems caused by functional or implicit forms. Parametric curves replace the use of geometric slopes, which may be infinite, with parametric tangent vectors, which we shall see are never infinite. Here a curve is approximated by a piecewise polynomial curve. Each segment q of the overall curve is given by the three functions x, y, and z, which are cubic polynomials in the parameter t. Cubic polynomials are most often used because lower degree polynomials give too little flexibility in controlling the shape of the curve, and higher degree polynomials can introduce unwanted wiggles and also require more computation. No lower degree representation allows a curve segment to interpolate pass through two specified endpoints with specified derivatives at each endpoint. Given a cubic polynomial with its four coefficients, four knowns are used to solve for the unknown coefficients. The four knowns might be the two endpoints and the derivatives at the endpoints. Similarly, the two coefficients of a first-order straight-line polynomial are determined by the two endpoints. For a straight line, the derivatives at each end are determined by the line itself and cannot be controlled independently. With quadratic second-degree polynomials and hence three coefficients, two endpoints and one other condition, such as a slope or additional point, can be specified. Also, the parametric cubics are the lowest degree curves that are non-planar in 3D. You can see this by recognizing that as second-order polynomials, three coefficients can be completely specified by 3 points, and that 3 points define a plane in which the polynomial lies. Higher degree curves require more conditions to determine the coefficients and can wiggle back and forth in ways that are difficult to control. Despite this, higher degree curves are used in applications such as the design of cars and planes, in which higher degree derivatives must be controlled to create surfaces that are aerodynamically efficient. In fact, the mathematical development for parametric curves and surfaces is often given in terms of an arbitrary degree n. In this chapter, we fix n at 3. The cubic polynomials that define a curve segment q of t equals x of t, y of t, z of t are of the form shown below. We can rewrite the above equation as q of t equals x of t, y of t, z of t equals t and c. To deal with the finite segments of the curve without loss of generality, we restrict the parameter t to the 0, 1 interval. With capital T equals t cubed t squared t 1, and defining the matrix of coefficients of the three polynomials as shown below. This figure shows two joint parametric cubic curve segments and their polynomials. It also illustrates the ability of parametrics to represent easily multiple values of y for a single value of x with polynomials that are themselves single-valued. In this figure, the dashed lines between the xy plot and the xt and yt plots show the correspondence between the points on the xy curve and the defining cubic polynomials. The xt and yt plots for the second segment have been translated to begin at t equals 1 rather than at t equals 0 to show the continuity of the curves at their join point. The derivative of q of t is the parametric tangent vector of the curve, as shown in the equation below. If two curve segments join together, the curve has G0 geometric continuity. If the directions, but not necessarily the magnitudes, of the two segments' tangent vectors are equal at a join point, the curve has G1 geometric continuity. In computer-aided design of objects, G1 continuity between curve segments is often required. G1 continuity means that the geometric slopes of the segments are equal at the join point. For two tangent vectors TV1 and TV2 to have the same direction, it is necessary that one be a scalar multiple of the other. TV1 equals k and TV2, with k being greater than 0. If the tangent vectors of the two cubic curve segments are equal, that is, their directions and magnitudes are equal. At the segment's join point, the curve has first-degree continuity in the parameter t or parametric continuity and is said to be C1 continuous. If the direction and magnitude of d power n over dt power n into q of t through the nth derivative are equal at the join point, the curve is called Cn continuous. This figure shows curves with 3 different degrees of continuity. Note that a parametric curve segment is itself everywhere continuous. The continuity of concern here is at the join points. This figure shows curve segment S joined to segments C0, C1 and C2 with the 0, 1 and 2 degrees of parametric continuity respectively. The visual distinction between C1 and C2 is slight at the join but obvious away from the join. The tangent vector q-t is the velocity of a point on the curve with respect to the parameter t. Similarly, the second derivative of q of t is the acceleration. If a camera is moving along the parametric cubic curve in equal time steps and records a picture after each step, the tangent vector gives a velocity of the camera along the curve. The camera velocity and acceleration at join points should be continuous to avoid jerky movements in the resulting animation sequence. It is this continuity of acceleration across a join point in this figure that makes the C2 curve continue farther to the right than the C1 curve before bending around to the end point. In general, C1 continuity implies G1, but the converse is generally not true. That is, G1 continuity is generally less restrictive than C1, so curves can be G1 but not necessarily C1. However, join points with G1 continuity will appear just as smooth as those with C1 continuity, as seen in this figure. This figure shows curve segments Q1, Q2 and Q3 joining at the point P2 and are identical except for the tangent vectors at P2. Q1 and Q2 have equal tangent vectors and hence are both G1 and C1 continuous at P2. Q1 and Q3 have tangent vectors in the same direction, but Q3 has twice the magnitude, so they are only G1 continuous at P2. The larger tangent vector of Q3 means that the curve is pulled more in the tangent vector direction before heading toward P3. Vector TV2 is the tangent vector of Q2. TV3 is that for Q3. There is a special case in which C1 continuity does not imply G1 continuity. When both segments' tangent vectors are 0, 0, 0 at the join point. In this case, the tangent vectors are indeed equal, but their directions can be different as per the figure shown. This figure shows the one case for which C1 continuity does not imply G1 continuity. The tangent vector, that is the parametric velocity along the curve, is 0 at the join point P. Each tick mark shows a distance moved along the curve in equal time intervals. As the curve approaches P, the velocity goes to 0, then increases past P. This figure shows the concept in another way. Think again of a camera moving along the curve. Camera velocity slows down to 0 at the join point. Camera changes direction while its velocity is 0, and the camera accelerates in the new direction. Figure A shows a view of a 2D parametric cubic curve in 3D, x, y, t space, and B, the curve in 2D. At the join, the velocity of both parametrics is 0. That is, dy over dt is 0, and dx over dt is also 0. You can see this by noting that at the join, the curve is parallel to the t-axis, so there is no change in either x or y. Yet at this join point, the parametrics are C1 continuous, but are not G1 continuous. The plot of a parametric curve is distinctly different from the plot of an ordinary function, in which the independent variable is plotted on the x-axis and the dependent variable is plotted on the y-axis. In parametric curve plots, the independent variable t is never plotted at all. This means that we cannot determine, just by looking at a parametric curve plot, the tangent vector to the curve. It is possible to determine the direction of the vector, but not its magnitude. This can be seen as follows. If gamma of t, with t lying between or equal to 0 and 1, is a parametric curve, its tangent vector at time 0 is gamma dash 0. If we let eta of t equals gamma of 2t, with t lying between or equal to 0 and half, then the parametric plots of gamma and eta are identical. On the other hand, eta dash 0 equals 2 gamma dash 0. Thus, two curves that have identical plots can have different tangent vectors. This is the motivation for the definition of geometric continuity. For two curves to join smoothly, we require only that their tangent vector directions match, not that their magnitudes match. A curve segment Q of t is defined by constraints on endpoints, tangent vectors, and continuity between curve segments. Each cubic polynomial has 4 coefficients, so 4 constraints would be needed, allowing us to formulate 4 equations in the 4 unknowns, then solving for the unknowns. The 3 major types of curves are Hermite curves, Bicubic curves, and splines. Hermite defined by 2 endpoints and 2 endpoint tangent vectors. Bicubic defined by 2 endpoints and 2 other points that control the endpoint tangent vectors, and several kinds of splines, each defined by 4 control points. The splines have C1 and C2 continuity at the joint points and come close to their control points, but generally do not interpolate the points. Types of splines are uniform B-splines, non-uniform B-splines, and beta splines. A parametric cubic curve is defined by Q of t equals t and c. We rewrite the coefficient matrix as C equals M and G, where M is a 4 cross 4 basis matrix and G is a 4-element column vector of geometric constraints called the geometry vector. The geometric constraints are just the conditions such as endpoints or tangent vectors that define the curve. We use Gx to refer to the column vector of just the x components of the geometry vector. Gy and Gz have similar definitions. M or G or both M and G differ for each type of curve. The elements of M and G are constants, so that product T into M into G is just 3 cubic polynomials in T. Expanding the product Q of T, T and M and G gives the matrix given below. Multiplying out just x of t equals t and m and gx gives the equation as shown. The weights are each cubic polynomials of t and are called blending functions. The blending functions b are given by b equals t and m. Notice the similarity to a piecewise linear approximation, for which only 2 geometric constraints, the endpoints of the line, are needed. So each curve segment is a straight line defined by the endpoints g1 and g2. X of t equals g1x of 1 minus t plus g2x of t. Y of t equals g1y of 1 minus t plus g2y of t. Z of t equals g1z of 1 minus t plus g2z of t. Parametric cubics are really just a generalization of straight line approximations. Plane equations. When working with polygons or polygon meshes, we frequently need to know the equation of the plane in which the polygon lies. In some cases, of course, the equation is known implicitly through the interactive construction methods used to define the polygon. If it is not known, we can use the coordinates of 3 vertices to find the plane. Recall the plane equation ax plus by plus cz plus d equals 0. The coefficients a, b and c define the normal to the plane ABC. Given points p1, p2 and p3 on the plane, that plane's normal can be computed as a vector cross product p1, p2 into p1, p3 or p2, p3 cross p2, p1, etc. If the cross product is 0, then the 3 points are collinear and do not define a plane. Other vertices, if any, can be used instead. Given a non-zero cross product, D can be found by substituting the normal A, B, C and any of the 3 points into the above equation. If there are more than 3 vertices, they may be non-planar, either for numerical reasons or because of the method by which the polygons were generated. Then another technique for finding the coefficients A, B and C of a plane that comes close to all the vertices is better. It can be shown that A, B, and C are proportional to the signed areas of the projections of the polygon onto the YZ, XZ, and XY planes, respectively. For example, if the polygon is parallel to the XY plane, then A equals B equals 0, as expected. The projections of the polygon onto the YZ and XZ planes have 0 area. This method is better because the areas of the projections are a function of the coordinates of all the vertices and so are not sensitive to the choice of a few vertices that might happen not to be coplanar with most or all of the other vertices, or that might happen to be collinear. For instance, the area and hence coefficient C of the polygon projected onto the XY plane in this figure is just the area of the trapezoid A3 minus the areas of A1 and A2. Calculating the area C of a triangle. In general, the area C is calculated as follows, where the operated circle plus is normal addition except that n circle plus 1 equals 1. The areas for A and B are given by similar formulae except the area for B is negated. The above equation gives the sum of the areas of all the trapezoids formed by successive edges of the polygons. If xi circle plus 1 is less than xi, the area makes a negative contribution to the sum. The sign of the sum is also useful. If the vertices have been enumerated in a clockwise direction as projected onto the plane, then the sign is positive. Otherwise, it is negative. Once we determine the plane equation by using all the vertices, we can estimate how non-planar the polygon is by calculating the perpendicular distance from the plane to each vertex. This distance d for the vertex at x, y, z is d equals ax plus by plus cz plus d over square root of a squared plus b squared plus c squared. This distance is either positive or negative depending on which side of the plane the point is located. If the vertex is on the plane, then d equals 0. Of course, to determine only on which side of the plane a point is, only the sign of d matters, so division by the square root is not needed. The plane equation is not unique. Any non-zero multiplicative constant k changes the equation but not the plane. It is often convenient to store the plane coefficients with a normalized normal. This can be done by choosing k as follows. K equals 1 over square root of a squared plus b squared plus c squared, which is the reciprocal of the length of the normal. Then distances can be computed more easily since the denominator is 1. Polygon meshes representing curves and surfaces. The three most common representations for 3D surfaces are polygon mesh surfaces, parametric surfaces, quadric surfaces. Parametric surfaces are a simple generalization of the curves. Polygon mesh. A polygon mesh is a set of connected polygonally bounded planar surfaces. Open boxes, cabinets, and building exteriors can be easily and naturally represented by polygon meshes, as can volumes bounded by planar surfaces. Polygon meshes can be used, although less easily, to represent objects with curved surfaces, as in this figure, a 3D object represented by polygons. However, the representation is only approximate. This figure shows a cross-section of a curved shape and the polygon mesh representing it. A cross-section of a curved object and its polygonal representation. The obvious errors in the representation can be made arbitrarily small by using more and more polygons to create a better piecewise linear approximation, but this increases space requirements and the execution time of algorithms processing the representation. Furthermore, if the image is enlarged, the straight edges again become obvious. Parametric polynomial curves define points on a 3D curve by using three polynomials in a parameter t1 for each x, y, and z. The coefficients of the polynomials are selected such that the curve follows the desired path. Cubic polynomials that have powers of the parameter up through the third. The term cubic curve will often be used for such curves. Parametric bivariate, two-variable. Polynomial surface patches define the coordinates of points on a curved surface by using three bivariate polynomials, one for each of x, y, and z. The boundaries of the patches are parametric polynomial curves. Many fewer bivariate polynomial surface patches than polygonal patches are needed to approximate a curved surface to a given accuracy. The algorithms for working with bivariate polynomials are more complex than are those for polygons. The surfaces are accordingly called bicubic surfaces. Quadric surfaces are those defined implicitly by an equation function x, y, z equals 0, where f is a quadric polynomial in x, y, and z. Quadric surfaces are a convenient representation for the familiar sphere, ellipsoid, and cylinder. Polygon meshes. A polygon mesh is a collection of edges, vertices, and polygons connected such that each edge is shared by at most two polygons. An edge connects two vertices and a polygon is a closed sequence of edges. An edge can be shared by two adjacent polygons, and a vertex is shared by at least two edges. The application programmer's task is to choose the most appropriate representation. Several representations can be used in a single application, one for external storage, another for internal use, and yet another with which the user interactively creates the mesh. Two basic criteria, space and time, can be used to evaluate different representations. Typical operations on a polygon mesh are finding all the edges incident to a vertex, finding the polygons sharing an edge or a vertex, finding the vertices connected by an edge, finding the edges of a polygon, displaying the mesh, and identifying the errors in representation, for example, a missing edge, vertex, or polygon. In general, the more explicitly the relations among polygons, vertices, and edges are represented, the faster the operations are and the more space the representation requires. Representing polygon meshes ensures that a given representation is correct and calculating the coefficients of the plane of a polygon. Representing polygon meshes. Polygon mesh representations. 1. Explicit representation. 2. Pointers to a vertex list representation. 3. Pointers to an edge list representation. Explicit representation. In the explicit representation, each polygon is represented by a list of vertex coordinates as shown here. The vertices are stored in the order in which they would be encountered traveling around the polygon. There are edges between successive vertices in the list and between the last and first vertices. For a single polygon, this is space efficient. For a polygon mesh, much space is lost because the coordinates of shared vertices are duplicated. Even worse, there is no explicit representation of shared edges and vertices. For instance, to drag a vertex and all its incident edges interactively, we must find all polygons that share the vertex. This requires comparing the coordinate triples of the one polygon with those of all other polygons. The most efficient way to do this would be to sort all n coordinate triples, but this is at best an n log 2n process, and even then there is the danger of the same vertex might, due to computational roundoff, have slightly different coordinate values in each polygon, so a correct match might never be made. With this representation, displaying the mesh either as filled polygons or as polygon outlines necessitates transforming each vertex and clipping each edge of each polygon. If edges are being drawn, each shared edge is drawn twice. This causes problems on pen plotters, film recorders, and vector displays due to the overwriting. A problem may also be created on raster displays if the edges are drawn in opposite directions, in which case extra pixels may be intensified. Pointers to a vertex list representation. Polygons defined with pointers to a vertex list, the method used by sfix, have each vertex in the polygon mesh stored just once. In the vertex list, V equals x1, y1, z1, going up to xn, yn, zn. A polygon is defined by a list of indices or pointers into the vertex list. For example, if a polygon made up of vertices 3, 5, 7, and 10 in the vertex list would thus be represented as P equals 3, 5, 7, 10. This representation, an example of which is shown in this figure, has several advantages over the explicit polygon representation. Polygon mesh defined with indexes into a vertex list. Since each vertex is stored just once, considerable space is saved. The coordinates of a vertex can be changed easily. On the other hand, it is still difficult to find polygons that share an edge, and shared polygon edges are still drawn twice when all polygon outlines are displayed. These two problems can be eliminated by representing edges explicitly, as in pointers to an edge list representation. Pointers to an edge list representation. When defining polygons by pointers to an edge list, we again have the vertex list V, but represent a polygon as a list of pointers, not to the vertex list, but rather to an edge list, in which each edge occurs just once. In turn, each edge in the edge list points to the two vertices in the vertex list, defining the edge, and also to the one or two polygons to which the edge belongs. Hence, we describe a polygon as P equals E1 going up to En, and an edge as E equals V1, V2, P1, P2. When an edge belongs to only one polygon, either P1 or P2 is null. This figure shows an example of this representation. Polygon mesh defined with edge lists for each polygon. Lambda represents null. Polygon outlines are shown by displaying all edges rather than by displaying all polygons. Thus, redundant clipping, transformation, and scan conversion are avoided. Filled polygons are also displayed easily. In such cases, the edge descriptions can be extended to include an arbitrary number of polygons, E equals V1, V2, P1, P2, going up to Pn. In none of these three representations, that is, explicit polygons, pointers to vertices, pointers to an edge list, is it easy to determine which edges are incident to a vertex. All edges must be inspected. Of course, information can be added explicitly to permit determining such relationships. For instance, the winged edge representation used by Baumgart expands the edge description to include pointers to the two adjoining edges of each polygon, whereas the vertex description includes a pointer to an arbitrary edge incident on the vertex, and thus more polygon and vertex information is available. Consistency of polygon mesh representations. Polygon meshes are often generated interactively, such as by operators digitizing drawings, so errors are inevitable. Thus, it is appropriate to make sure that all polygons are closed, all edges are used at least once, but not more than some application-defined maximum, and each vertex is referenced by at least two edges. In some applications, we would also expect the mesh to be completely connected. Any vertex can be reached from any other vertex by moving along the edges. To be topologically planar, the binary relation on vertices defined by edges can be represented by a planar graph. Or to have no holes, there exists just one boundary, a connected sequence of edges, each of which is used by one polygon. Of the three representations discussed, the explicit edge scheme is the easiest to check for consistency because it contains the most information. For example, to make sure that all edges are part of at least one but not more than some maximum number of polygons, the code in this figure can be used, as shown. This procedure is by no means a complete consistency check. For example, an edge used twice in the same polygon goes undetected. A similar procedure can be used to make sure that each vertex is part of at least one polygon. We check whether at least two different edges of the same polygon refer to the vertex. Also, it should be an error for the two vertices of an edge to be the same unless edges with zero length are allowed. The relationship of sharing an edge between polygons is a binary equivalence relation, and hence partitions a mesh into equivalence classes called connected components. More detailed testing is also possible. One can check, for instance, that each polygon referred to by an edge E1 refers in turn back to the edge EI. This ensures that all references from polygons to edges are complete. Similarly, we can check that each edge EI referred to by a polygon PI also refers back to polygon PI, which ensures that the reference from edges to polygons are complete. Subdividing curves. Suppose you have just created a connected series of curve segments to approximate a shape you are designing. You manipulate the control points, but you cannot quite get the shape you want. Probably there are not enough control points to achieve the desired effect. There are two ways to increase the number of control points. One is the process of degree elevation. The degree of the splines is increased from 3 to 4 or more. This adjustment is sometimes necessary, especially if higher orders of continuity are needed, but is generally undesirable because of the additional inflection points allowed in a single curve and the additional computational time needed to evaluate the curve. The second, more useful way to increase the number of control points is to subdivide one or more of the curve segments into two segments. For instance, a Bezier curve segment with its 4 control points can be subdivided into two segments with a total of 7 control points. The two new segments share a common point. The two new segments exactly match the one original segment until any of the control points are actually moved. Then one or both of the new segments no longer matches the original. For non-uniform B-splines, a more general process known as refinement can be used to add an arbitrary number of control points to a curve. Another reason for subdividing is to display a curve or surface. Given a Bezier curve Q of t defined by points P1, P2, P3 and P4, we want to find a left curve defined by points L1, L2, L3 and L4 and a right curve defined by points R1, R2, R3 and R4, such that the left curve is coincident with Q on the interval 0 is less than or equal to t is less than 1 by 2, and the right curve is coincident with Q on the interval 1 by 2 is less than or equal to t is less than 1. The subdivision can be accomplished using a geometric construction technique to evaluate a Bezier curve for any value of t. The point on the curve for a parameter value of t is found by drawing the construction line L2H so that it divides P1, P2 and P2, P3 in the ratio of t is to 1 minus t, HR3 so that it similarly divides P2, P3 and P3, P4 and L3, R2 to likewise divide L2H and HR3. The point L4, which is also R1, divides L3, R2 by the same ratio and gives a point QT. This figure shows the construction for 1 equals 1 by 2, the case of interest. This figure shows the Bezier curve defined by the points Pi is divided at t equals 1 by 2 into a left curve defined by the points Li and a right curve defined by the points Ri. All the points are easy to compute with an add and shift to divide by 2 per equation shown. These results can be reorganized into matrix form so as to give the left Bezier division matrix DLB and the right Bezier division matrix DRB. These matrices can be used to find the geometry matrices GLB of points for the left Bezier curve and GRB for the right Bezier curve as shown. Notice that each of the new control points Li and Ri is a weighted sum of the points Pi with the weight positive and summing to 1. Thus each of the new control points is in the convex hull of the set of original control points. Therefore the new control points are no farther from the curve Q of t than are the original control points, and in general are closer than the original points. This variation diminishing property is true of all splines that have the convex hull property. Also, notice the symmetry between DLB and DRB, a consequence of the symmetry in the geometrical construction. Dividing the Bezier curve at t equals 1 by 2 often gives the interactive user the control needed, but it might be better to allow the user to indicate a point on the curve at which a split is to occur. Given such a point, it is easy to find the approximate corresponding value of t. The splitting then proceeds as described previously, except that the construction lines are divided in the t is to 1 minus t ratio. The corresponding matrices DLBS and DRBS for the B-spline subdivision are as shown. Careful examination of these two equations show that the 4 control points of GLBS are replaced by a total of 5 new control points shared between GLBSI and GRBSI. However, the spline segments on either side of the one being divided are still defined by some of the control points of GBSI. Thus, changes to any of the 5 new control points or 4 old control points cause the B-spline to be no longer connected. This problem is avoided with non-uniform B-splines. Subdividing non-uniform B-splines is not as simple as specifying 2 splitting matrices because there is no explicit basis matrix. The basis is defined recursively. The basic approach is to add knots to the knot sequence. Given a non-uniform B-spline defined by the control points P0 to Pn and a value of t equals t dash at which to add a knot and hence to add a control point, we want to find the new control points Q0 going up to Qn plus 1 that define the same curve. The value t dash satisfies Tj is less than t dash is less or equal to Tj plus 1. Bohm has shown that the new control points are given by the equation shown, where Ai is given by the equation shown. This algorithm is a special case of the more general Oslo algorithm, which inserts any number of knots into a B-spline in a single set of computations. If more than a few knots are being inserted at once, the Oslo algorithm is more efficient than is the Bohm algorithm. As an example of Bohm subdivision, consider the knot sequence knot 1 1 1 1. The 4 x coordinates of the control point vector 5.0, 8.0, 9.0 and 6.0 and a new knot at t equals 0.5, that is n equals 3, j equals 3. The ai values are 0.5, 0.5, 0.5. We find that the x coordinates of the new qi control points are 5.0, 6.5, 8.5, 7.5 and 6.0. Notice that adding a knot causes 2 old control points to be replaced by 3 new control points. Furthermore, segments adjacent to the subdivided segment are defined only in terms of the new control points. Contrast this to the less attractive case of uniform B-spline subdivision in which 4 old control points are replaced by 5 new ones and adjacent segments are defined with the old control points which are no longer used for the 2 new segments. Hierarchical B-spline refinement is another way to gain finer control over the shape of a curve. Additional control points are added to local regions of a curve, and a hierarchical data structure is built relating to the new control points to the original control points. Use of the hierarchy allows further additional refinement. Storing the hierarchy rather than replacing the old control points with a larger number of new control points means that the original control points can continue to be used for coarse overall shaping of the curve, while at the same time the new control points can be used for control of details. Uniform non-rational B-splines. The term spline goes back to the long flexible strips of metal used by draftspersons to lay out the surfaces of airplanes, cars and ships. Ducks weights attached to the splines were used to pull the spline in different directions. The metal splines, unless severely stressed, had second-order continuity. The mathematical equivalent of these strips, the natural cubic spline, is a C0, C1 and C2 continuous cubic polynomial that interpolates or passes through the control points. This is one more degree of continuity than is inherent in the Hermite and Bezier forms. The splines are inherently smoother than are the previous forms. The polynomial coefficients for natural cubic splines, however, are dependent on all n control points. Their calculation involves inverting an n plus 1 by n plus 1 matrix. This has 2 disadvantages. Moving any one control point affects the entire curve, and the computation time needed to invert the matrix can interfere with the rapid interactive reshaping of a curve. B-splines consist of curve segments whose polynomial coefficients depend on just a few control points. This is called local control. Thus, moving a control point affects only a small part of the curve. In addition, the time needed to compute the coefficients is greatly reduced. B-splines have the same continuity as natural splines, but do not interpolate their control points. A curve segment need not pass through its control points, and the two continuity conditions on a segment come from the adjacent segments. This is achieved by sharing control points between segments, so it is best to describe the process in terms of all the segments at once. Cubic B-splines approximate a series of m+1 control points, P0 going up to Pm, m being greater or equal to 3, with a curve consisting of m-2 cubic polynomial curve segments Q3, Q4, Qm. Although such cubic curves might be defined each on its own domain, with 0 less than or equal to t less than 1, we can adjust the parameter, making a substitution of the form t equals t plus k, so that the parameter domains for the various curve segments are sequential. Thus we say that the parameter range on which Qi is defined as Ti is less than or equal to t is less than Ti plus 1 for I lying between 3 and m. In the particular case of m equals 3, there is a single curve segment Q3 that is defined on the interval T3 is less than or equal to t less than T4 by 4 control points P0 to P3. For each I greater or equal to 4, there is a join point or knot between Qi-1 and Qi at the parameter value Ti. The parameter value at such a point is called a knot value. The initial and final points at T3 and Tm+1 are also called knots, so that there is a total of m-1 knots. This figure shows a 2D B-spline curve with its knots marked. A closed B-spline curve is easy to create. The control points P0, P1, P2 are repeated at the end of the sequence P0, P1 going up to Pm, P0, P1, P2. The term uniform means that the knots are spaced at equal intervals of the parameter t. Without loss of generality, we can assume that T3 equals 0 and the interval Ti plus 1 minus Ti equals 1. Non-uniform, non-rational B-splines which permit unequal spacing between the knots. The term non-rational is used to distinguish these splines from rational cubic polynomial curves, where x of t, y of t, and z of t are each defined as a ratio of two cubic polynomials. The B stands for basis, since the splines can be represented as weighted sums of polynomial basis functions, in contrast to the natural splines, for which this is not true. Each of the m-2 curve segments of a B-spline curve is defined by 4 of the m+1 control points. In particular, curve segment Qi is defined by points Pi-3, Pi-2, Pi-1, and Pi. Thus, the B-spline geometry vector GBSI for segment Qi is as shown below. The first curve segment Q3 is defined by the points P0 through P3 over the parameter range T3 equals 0 to T4 equals 1. Q4 is defined by the points P1 through P4 over the parameter range at T4 equals 1 to T5 equals 2. And the last curve segment Qm is defined by the points Pm-3, Pm-2, Pm-1, and Pm over the parameter range Tm equals m-3 to Tm plus 1 equals m-2. In general, curve segment Qi begins somewhere near point Pi-2 and ends somewhere near points Pi-1. We shall see that the B-splines blending functions are everywhere non-negative and sum to unity, so the curve segment Qi is constrained to the convex hull of its 4 control points. Just as each curve segment is defined by the 4 control points, each control point, except for those at the beginning and end of the sequence P0 going up to Pm, influences 4 curve segments. Moving a control point in a given direction moves the 4 curve segments it affects in the same direction. The other curve segments are totally unaffected. See the figure. If we define Ti as a row vector, t minus ti cubed, t minus ti squared, t minus ti 1, then the B-spline formulation for the curve segment I will appear as shown. The B-spline basis matrix MBS relates the geometrical constraints of GBS to the blending functions and the polynomial coefficients, as shown. The B-spline blending functions BBS are given by the product TI and MBS analogously to the previous Bezier and Hermite formulations. Note that the blending functions for each curve segment are exactly the same because for each segment I, the values of t minus ti range from 0 at t equals ti to 1 at t equals ti plus 1. This figure shows the B-spline blending functions BBS. Because the four functions sum to 1 and are non-negative, the convex hull property holds for each curve segment of a B-spline. This figure shows the effect of multiple control points at the interior of a B-spline. The price of interpolating the points in part C is loss of G1 continuity. This is the case where C1 continuity does not imply G1 continuity. The effect of multiple control points on a uniform B-spline curve is shown in these figures. In A, there are no multiple control points. The convex hulls of the two curves overlap. The join point between Q3 and Q4 is in the region shared by both convex hulls. In B, there is a double control point, so that two convex hulls share edge P2 at P3. The join point is therefore constrained to lie on this edge. In C, there is a triple control point, and the two convex hulls are straight lines that share the triple point. Hence, the join point is also at the triple point. Because the convex hulls are straight lines, the two curve segments must also be straight lines. There is C2 but only G0 continuity at the join. Problem. Show that the knot set used in constructing the Bezier B-spline approximation to a guiding polyline guarantees that the endpoints of the spline coincide with the endpoints of the guiding polyline. Solution. For an m-degree Bezier B-spline approximation, the knot set used appears as shown. Let P0, X0, Y0, Z0 be the first control point of the guiding polyline, and Pn, Xn, Yn, Zn the last. Now x of t equals sigma I equals 0 to n of xi, bi, m into t, with similar expressions for y of t and z of t. We wish to show that x0 is equal to x0, y0 equal to y0, and z0 equal to z0, and x into n minus 1 equals xn, y into n minus 1 equals yn, and z into n minus 1 equals zn. Let us restrict ourselves to m equals 2 quadratic B-splines. Then the knot set is as shown. Since bi2 of x is non-zero, only over the interval ti less than equal to x is less than or equal to ti plus 3, it follows that bi, 2 naught is non-zero only if I equals 0, 1 and 2. So then, the equation x0 will appear as shown. To calculate b0, 2 using the definition and the convention that 0 by 0 equals 0, we obtain b0 to 0 equals to b110 and b110 equals b200 and b200 equals 1. So b02 of 0 equals 1. To calculate b12 of 0 using the definition as shown. So we have b12 of 0 equals 0. In a similar manner, we find that b2 of 2 of 0 equals 0. Thus, x0 is equal to x0, and the same for the y and z coordinates. Similar calculations show that x into n minus 1 equals xn, y into n minus 1 equals yn, and z into n minus 1 equals zn. Problem. Show that the nth degree B-spline basis functions bin x satisfy bin of x equals 0 if x is less than ti or x is greater than ti plus n plus 1. Solution. Since the B-spline basis functions bin of x are defined recursively in terms of the lower order B-splines bin-1x and bi plus 1 n-1x of degree n-1, we shall indicate only the first step of a general induction argument. Therefore, we illustrate what happens for the first degree B-spline bi1 of x. Now suppose that x is less than ti, then also x is less than ti plus 1. So at x the 0 degree B-splines have the values bi naught of x equals 0 and bi plus 1, 0, x equals 0. From these values we find in turn that bi plus 1 x equals 0. Now suppose that the knot set is non-repeating. Let x equal to ti. Then bi naught of ti equals 1, but bi plus 1 naught into ti is equal to 0. So the below equation results. Thus bi1 of x equals 0 if x is less than or equal to ti. Similar arguments show that bi1 of x equals 0 if x is greater or equal to ti plus 1. Problem. Let p0 0, 0, p1 1, 2 and p2 2, 1 and p3 3, -1 and p4 4, 10 and p5 5, 5 be given data points. If interpolation based on cubic B-splines is used to find a curve, interpolating these data points, find a knot set T0 to T9 that can be used to define the cubic B-splines. Solution. Choose T0 equals T1 equals T2 equals T3 equals -1, which is less than x0, and T6 equals T7 equals T8 equals T9 equals 6, which is greater than xn. The remaining knots are chosen according to the formula ti plus m plus 1 equals xi plus 1 plus xi plus m over m, I equals 0 going up to n minus m minus 1. So T4 equals 1 plus 2 plus 3 over 3 equals 2. T5 equals 2 plus 3 plus 4 over 3 equals 3. An alternative scheme for cubic splines is T0 equals T1 equals T2 equals T3 equals -1 and T6 equals T7 equals T8 equals T9 equals 6, and the remaining knots are chosen according to Ti plus 4 equals xi plus 2, I equals 0 going up to n minus 4. So T4 equals 2, T5 equals 3. The agreement between knot sets chosen according to these two schemes is the result of the uniform spacing of the data points along the x-axis. Problem. Write the equations that can be used to find an interpolating cubic spline curve to fit the data p0, 0, 0, p1, 1, 2, p2, 2, 1, p3, 3, -1, p4, 4, 10, and p5, 5, 5, using cubic B-spline basis functions. Solutions. With m equals 3 and n equals 5, the interpolating spline can be written in terms of cubic B-splines as shown. The interpolation equations for the data points xj, yj with j equals 0 going up to 5 are yj equals s3 of xj with j equals 0 going up to 5. With the knot set chosen in previous problem, the intervals tj, tj plus 4 is defined by the knots tj, where j equals 0 going up to 9. And the following matrix results. Because bi, 3 of x is non-zero, only for ti is less than x is less than ti plus 4, the interpolation equations become yj equals s3 of xj. And the other equations follow as shown on the screen. The remaining two equations can be chosen to satisfy prescribed boundary conditions at x0 equals 0 and x5 equals 5. Conclusion. In this chapter, we have covered the following in detail. Polygon meshes, representing polygon meshes, consistency of polygon mesh representations, plane equations, parametric cubic curves, Hermite curves, Bezier curves, uniform non-rational B-splines, subdividing curves, drawing curves, comparison of the cubic curves, parametric bicubic surfaces.